Up to this point, most of the systems we've been looking at have exactly one unique solution. And we hinted at this earlier, but that's not always going to be the case. Sometimes a system will have one unique solution, but other times the system will have no solutions or it'll have many solutions. So there are always three possibilities when you're dealing with a linear system: one solution, no solutions, or infinitely many solutions. And in this video, I want to look at how you determine how many solutions there are to the system. So when you've been given a linear system, and in this one, we'll look at this particular matrix. So we have a linear system of three equations in three unknowns, and we've already put that system into a matrix. So for instance, this first row represents the equation x minus y plus 2z is equal to -3. The second row represents 4x plus 4y minus 2z equals 1. You get the idea. So we have that system set up in the matrix. In order to solve the system, we're going to use Gauss-Jordan elimination to try to move the matrix toward reduced row echelon form. When we do that, we're always going to end up with one of three results. And keep in mind that this process is going to work for any matrix regardless of the dimensions of the matrix. In this case, we're looking at a 3x3 matrix because here on the left we have three equations in three unknowns. So it's a 3x3 matrix. If we're able to get this left-hand side here down to reduced row echelon form, such that we have these rows 1, 0, 0, 0, 1, 0, and 0, 0, 1, and this is the case that we've run into most often so far, then we know that the system has exactly one solution. It's x equals a, y equals b, and z equals c, and that's the solution to the system. The system has a solution, and it is this exact one unique solution. Sometimes, though, as we're working through Gauss-Jordan elimination, working this left-hand side toward reduced row echelon form, we end up with something that looks like this. A, B, and C are going to be non-zero entries. So maybe, for instance, we have 2, 4, and 6 over here on the right side for A, B, and C. But over here on the left, we have a normal-looking matrix, except for the bottom row here, we have all zeros. So when that's the case, remember we said A, B, and C are 2, 4, and 6, we would have x equals 2, y equals 4, and 0 equals 6. So right there, we see a problem. We can't possibly have 0 equals 6. That equation doesn't make sense. It's not true, which tells us that there's an inconsistency in the system. And in fact, we call this an inconsistent system. There are no solutions to the system because it can't possibly be true that 0 equals 6. So if you end up with a 0 row at the bottom and this C over here is a non-zero entry, you're saying a 0 value is equal to a non-zero value. That can't be true. There are no solutions to the system. If you end up with this situation where you have a complete 0 row at the bottom, so you have all zeros here on the bottom row on the left side, and you have a 0 value over here on the right-hand side, in other words, C is equal to 0, you've got a 0 over here, the entire row is full of zeros, that means you have infinitely many solutions. Because really, if this is a system in x, y, and z, you're saying x is equal to a, y is equal to b, those are fine, and then you're saying 0z is equal to 0. In other words, here I have 0z is equal to 0. That's what the last row is telling me. Well, as you can see here, I can set z equal to any value I want to. Z could be 1, 2, 3, 4, -7, 18, negative square root 2. It can be any value that I want it to be, and I'll still get 0 equals 0. The equation will still be true. So z can be any value, which means that there are going to be infinitely many solutions. You're going to have a defined value for x, which is a defined value for y, which is b, but then z can vary freely. It can be anything, which is why you're going to have infinitely many solutions with fixed x and y values and a z value that can vary to be any value. So when we're figuring out the number of solutions, we're just going to follow Gauss-Jordan elimination to get the matrix into reduced row echelon form. And once we get it there, we're going to see what kind of situation we have to determine whether or not we have one, none, or infinitely many solutions. So let's go through an example and work on this matrix here, which we already know represents a linear system of three equations in three unknowns. If we follow Gauss-Jordan elimination, notice that we already have a +1 as the pivot in the first row. So we're good there. Now we need to zero out the 2, 1, and 3, 1 positions, the 4 and the -2, to get zeros throughout the rest of the first column. So we'll do the row operation here. We'll say row 2 minus 4 times the first row, and we're going to use that value to replace row 2. When we do that, let's see what we get. So the first row is going to stay the same. We're going to have 1, -1, 2, and then -3. The second row will say 4 minus 4 times 1, or 4 minus 4 is 0. 4 minus 4 times -1 is 4 plus 4, or 8. -2 minus 4 times 2 is -2 minus 8, or -10. And then 1 minus 4 times a -3 is 1 plus 12, or 13. Now we need a 0 in the 3, 1 position where the -2 is. So let's do the row operation where we multiply the first row by 2 and add that to the third row. So we'll say 2 times row 1 plus row 3 is going to replace row 3. When we do that, we'll get 2 times 1 is 2, plus a -2 is 0. We'll get 2 times a -1 is a -2, plus 2 is 0. 2 times 2 is 4, plus -4 is 0. And then 2 times a -3 is a -6, plus 6 is 0. So already, without going any further, we can tell we have infinitely many solutions, because this last row of the matrix is a full 0 row, which matches this mini solutions matrix where we have zeros all across the bottom. So we know already the system's going to have infinitely many solutions. If we want to continue to simplify, we can do that continuing to work on the first and second rows. So let's go ahead and divide through the second row by 8, or multiply through the second row by 1/8. So that row operation will be 1/8 times row 2 is going to replace row 2. When we do that, the first row will stay the same, 1, -1, 2, and -3. The second row, 1/8 times 0 is 0. 1/8 times 8 is +1. 1/8 times a -10 is a -10/8, or a -5/4. And 1/8 times 13 is 13/8. And then our third row is still all zeros. Now, because we've got a pivot entry here in the second column, this +1, let's go ahead and zero out the rest of the second column. We can do that by adding the first and second rows and replacing the first row with that value. So we're going to say row 1 plus row 2 is going to replace row 1. That'll zero out this -1. So when we do that, we'll get 1 plus 0 is 1. -1 plus 1 is 0. 2 plus a -5/4, or 2 minus 5/4. Let's look at over here, 2 minus 5/4. If we multiply 2 by 4/4, we'll get 8/4 minus 5/4, or 3/4. So we'll get 3/4 here in the 1/3 position. And then we'll have -3 plus 13/8. So -3 plus 13/8. If we multiply the -3 by 8/8, we're going to get -24/8 plus 13/8. That'll give us a -11/8. So we'll say here -11/8, and then we'll have 0, 1, -5/4, 13/8, and then our row of zeros at the bottom. Now, other than the fact that this system has infinitely many solutions, this is the other really important point we want to make here. We know that the ones in these positions are pivot entries. They are the first non-zero entries in their rows, so they're the pivot entries, and we want those pivot entries equal to +1. Wherever you have a pivot entry, we call those columns pivot columns. So these columns here are pivot columns. Notice how if the third row is going to have another pivot entry, it would have to be right here where this 0 is. But there's no way that we can get this 0 to be some non-zero value and be a pivot entry. And there's nothing we can do about the 3/4 and the -5/4 here. So this is not a pivot column. This is what's called a free column. Every column in a matrix is either a pivot column or a free column. So these two are pivot columns because they have pivot entries. This column doesn't have a pivot entry, so it's called a free column. And the variables that each of these columns represent correspond to pivot and free. So these columns, if we say they represent X, Y, and Z, then X and Y are pivot variables and Z is a free variable since Z is in the free column and X and Y are in pivot columns. So we have pivot variables and free variables. And if we go ahead and translate this matrix back into a linear system, notice that from the first row here, we would get X, 1X, plus 0Y plus 3/4 Z is equal to -11/8. And then from the second row, we would get 0x plus 1y, so y, minus 5/4 z is equal to 13/8. Notice then that I can solve both of these equations for x and y. In other words, I can solve for my pivot variables. So I can say x is equal to -3/4 z minus 11/8. And I can say y is equal to 5/4 z plus 13/8. And this system here really illustrates why z is a free variable and why x and y are pivot variables. So I have my pivot variables solved for over here on the left side, and then I have my free variable over here on the right side of the equations. So notice that we could pick any value of z. For instance, we could pick z equals 0, and we would get certain values for x and y. I could pick z equals 5, and I would get a different value for x and y. I could pick z equals -2, and I would get a different value for x and y. So x and y are really depending on the value we pick for z, but the point is we can pick any value of z that we want to, and we'll still get valid solutions for x and y. So that's why we call z a free variable, because we can set it equal to any value that we choose, and we'll get a valid solution. On the other hand, x and y both depend on the value of z. So I couldn't just choose one value for x and a different value for y and automatically get a solution. If I did, I might get two different values for z, which isn't possible. Z obviously has to have its own consistent value, whatever value you're choosing at that time. So that's why z is a free variable and x and y are pivot variables. Later on, we're going to talk a lot more about how to express the solution here in terms of matrices. So it's really important for us to understand this idea of pivot variables versus free variables, and of course, to know how to determine whether the system has one solution, no solutions, or infinitely many solutions.